it's the greatest pleasure for me to introduce Wolfgang Ziller from the University of Pennsylvania. He has spent a long time here in Brazil. He even speaks Portuguese, so you can talk to him in Portuguese if you want. So he's going to talk about Finsler metrics, closed geodesics, and geodesics flow.
Thank you very much. So I also came to Brazil for the first time 15 years ago with Burkhard. Went to Goiânia and Brasilia, and Rio, and I've been back many times since then. So it's a real pleasure to give a talk here in São Paulo. Excuse me. There you go. Okay, so first I should say that this is joint work with Robert Bryant, Patrick Foulon, and Sergei Ivanov, and Vladimir Matveyev. So first I should maybe say that, well, before Perelman became famous, he gave a talk at Penn. This was when he still had long fingernails, right? And what he put on the blackboard was a letter X. And this was the only thing on the blackboard the rest of the talk. Well, X was a manifold, of course. For me, the manifolds are M and not X. I'll write down a little bit more on the blackboard. But first, let's have a conversation about closed geodesics. So this is a subject that's close to my heart. I started in this subject, proved existence and stability properties of closed geodesics. So the method in that subject is mainly variational theory of the energy function on the free loop space. Closed geodesics are critical point of this energy function, and one can try to use the topology of the free loop space to produce critical points of the energy function. Probably the oldest conjecture is that for every compact manifold, every metric has infinitely many closed geodesics. And that conjecture is still open, although by now one knows that this is true, except possibly in the case where the homology looks like that of a sphere or projective space. So for a sphere in general dimensions, one still only knows the existence of one, except for in dimension 2, where Bonnert and Franks proved that every metric has infinitely many. So the methods one uses, variation calculus, they work in a more general context in a very natural way. So if one looks at, say, Hamiltonian systems and tries to write down the variation problem for the shortest curves, it's well behaved when the metric is a Finsler metric. So what's a Finsler metric? It's something where in each tangent space, the unit sphere is a strictly convex body, which contains the origin also, but it doesn't have to be symmetric. So a unit sphere can look like some convex body. The origin can be over here. So the metric doesn't, a length of V doesn't have to be length of minus V. In fact, in many applications, that isn't in the case, that these are not symmetric. But since the unit sphere is strictly convex, geodesics have the same kind of properties as in Riemannian geometry. They are locally shortest connections. The variational theory on the free loop space works in the same way. It's a well-behaved variational problem. And most of the theorems in Riemannian geometry for the existence of Finsler metrics, for existence of closed geodesics on a Riemannian manifold, carry over with more or less the same proof also in Finsler geometry, except for the result in dimension 2 that I mentioned, since that's a combination of variational theory and the dynamics of the geodesic flow. and that's not known whether on the two-sphere there are infinitely many. In fact, when I worked on this subject, I went to Penn State and gave a talk on this subject, and then Katok pointed out to me that in the 70s he produced an example on the two-sphere, a Finsler metric on the two-sphere, which has only two closed geodesics. So I found that fascinating, and I started studying this example. I wanted to see how can you build up the topology of the free loop space with only two closed geodesics. And in particular, why should there be a reason that there should exist more than two in the Riemannian geometry, for Riemannian metric? So let me start out with describing that example, because that will again be important for us during the rest of the talk. So Katok example is in dimension 2, although this works in general dimensions. I start, let's say, with a Riemannian manifold. With all geodesics closed. And by normalizing, I can assume they have a common period. Let's say with common period 2 pi. So then I assume in addition that there exists a killing vector field. So let's X be killing. With flow, say, phi t. And without loss of generality, I can assume that this is also periodic, that phi 2 pi is equal to entity. If there exists one, I can always choose another one with this property. And now I can trust my Finsler matrix. I have to declare what the norm of a vector V is in the tangent bundle. And this will be the norm with respect to the Riemannian inner product plus the inner product between V and X in the Riemannian inner product. Okay. So this is not symmetric. Right? The vector length of V is not equal to minus V. In fact, if I were to draw the picture, I start with a round sphere. So this is a picture in the tangent space at every point. I start with a round sphere, and the effect is that X moves the origin. Right? So the origin, if this is a vector X here, the origin's over here. Okay. I'm going to put now a number alpha in front of it. So I want to have a one-parameter family of such Finsler metrics, which I put the alpha right here. And we'll see in a minute why that is useful. So I'm fixing X, but then I'm changing the amount that I move the origin in the unit sphere in this picture. So this here is F inverse of 1 in the tangent space. So a convex body. It's a Finsler metric. You can think, for example, as X being some kind of velocity vector field, maybe of a river or of wind, and you travel in a rowboat or an airplane. Right? Here it's important that alpha is not too large, otherwise the origin moves outside. So I have to assume that alpha is less than 1, then it's still a Finsler metric. Indeed, if you say travel in a river, you have to go from one side to the other side of the river with a rowboat, then this can always be done as long as X, which is the velocity of your river, is not too large. Indeed, I have to check that at every point for the water, the origin lies inside the unit sphere. If that's the case, I can go from any point of one side to any point of the other side. If the velocity is too large, of course, you're in trouble. So if you row, check that the origin is inside the unit sphere. Okay, so what properties does this metric have? Let's maybe look at a special example. So let's do this for a two-sphere. And X is dd phi in polar coordinates. So I'm rotating around the north and south pole, right? And then what do the geodesics in this new metric look like? I claim that the following form, the form t goes to, so I rotate with alpha t, because alpha is in front of the killing vector field x here. applied to gamma of t, where gamma of t is a geodesic in G0. In fact, this is a general statement. So in the general setup, that's always true, because the Killing vector field has a flow that acts by isometries, preserves the geodesics, and then it's not hard to see that geodesics are of this form. So in the two-sphere, I can draw a nice picture. Right? I just travel along great circles, and at the same time as I travel, I rotate. Where's the eraser for this blackboard? Here. I started rotating around the north and south pole at a constant speed, or a constant angle alpha. So I'm here, say, and I'm traveling in this direction by rotating. I follow the wind, if you want to. Right? So now notice that the behavior of this of the geodesic flow on this two-sphere depends on the value of alpha, the rotation right here. This rotates by alpha times t. So whether alpha is rational or not is important. Say if alpha is irrational, what does that mean? That means if I start at a longitude, I go along a great circle, I come back to the longitude, but with a shift of angle 2 pi alpha. That means it doesn't close up. So it means that the only two closures are on the equator. So in this situation, I have only two closed geodesics on the equator. And then you compute the length very easily. The length is 2 pi over 1 minus alpha, plus or minus alpha, depending on whether I travel with the wind around the equator or against it. Okay. So notice, say if alpha goes towards 1, the behavior is that one closed geodesic goes towards length pi, the other one wanders off to infinity. The energy function for this Morse function is a Morse-Bott function. So one can study the behavior of the critical points. It's not Morse-Bott. And one can actually see very nicely what kind of cancellations must take place in the free loop space in order to generate the homology. And in this case here, it says that in the free loop space, up to any type I want to, I can generate all the homology with a single closed geodesic. Okay. And you can see how it does that. But somewhere, eventually, a second one appears. So this example was very interesting for me. I was very excited to do various computations. You can compute the Poincare map, the index, and all kinds of properties. So the case I'm interested in today is actually the case where alpha is rational, which is interesting also for different reasons. So if alpha is p over q, so here I'm traveling at speed alpha, right, along the closed geodesics. That means that all geodesics are closed. Or of common length, 2 pi over q, 2 pi q. Right, if we travel along here up to 2 pi q and t is 2 pi q, then I end up at the same point. So they all have a common period, but they're exceptional ones. But there are two exceptional closed geodesics. In fact, at the same length there, so 2 pi over 1 plus or minus alpha, in this case would be 2 pi q, that's a common period, divided by p, and 2 pi q divided by p minus q. P is bigger, so remember alpha is small equal to 1. So these are the two exception closed geodesics. Already that phenomenon is interesting because in the Riemannian setting, if you have a metric on this 2 with all geodesics closed, they have a common period. There are no exception closed geodesics due to the theorem of Goldwasser model. So this is different in the Finsler setting, at least when the Finsler metric is non-symmetric. Okay, so this was a story that I studied in the 1980s, and what is new that was discovered eventually is the following property, that in the setup here, that the curvature of F alpha is the same as a curvature of F0. So here I don't even, so this is due to the fact that X is killing. I don't even need this condition. It has nothing to do with closed geodesics. And this was, I think, in this generality first observed by Foulon. In fact, he gave an ICM talk in 2004. And I think one of his interests was that you can also start, for example, with the Fubini studio metric on CPN. You're killing the form with some killing vector field, and the metric is 1/4 pinched and stays 1/4 pinched for this Finsler deformation. So there's no uniqueness of 1/4 pinched metrics on CPN in the realm of Finsler metrics, at least non-symmetric Finsler metrics. I think it's not known whether this is true for symmetric ones. So this property is now particularly interesting. So if F0 has curvature equal to 1, then also F alpha. So unlike in the Riemannian case, there are families of curvature 1 in the Finsler metric which are not standard. This was a long-standing open problem whether every Finsler metric of constant curvature is Riemannian. This is not the case, and then over the last 10 years or so, Robert Bryan wrote a sequence of papers with many examples of this type. In particular, the space of such metrics is infinite dimensional. There are lots of such examples, okay? Especially in dimension 2. So these are very nice papers. And the question is, what can one say about these metrics? What do they have in common? Can one say something about the geometry? So one of the theorems that I want to explain a little bit today is the following. Where's the other one went away. Okay. If I lose this one, I'm in trouble. Okay, so here's the following theorem. So if F is a Finsler metric on S2, with curvature constant equal to 1, then the conclusion is then the geodesic flow of F is determined by the length of the closed, or the shortest closed geodesic So by the geodesic flow here, I mean that I have my flow GT from the tangent bundle to the tangent bundle, which takes the tangent vector of the geodesic at time 0 into the tangent vector at time t. So that's called the geodesic flow. And by determined, I mean that if I have two Finsler metrics like this with the same smallest lengths, then there's a diffeomorphism of the tangent bundle that takes one to the other. So unique aptitude conjugacy. Okay. Although one should add that this is not quite as strong as one might think, because the diffeomorphism does not descend to the manifold. So I'm not saying that all geodesics on the manifold behaves exactly the same. I'm only saying the geodesic flow on the tangent bundle is the same. So a certain kind of uniform property among all these metrics that they share, and in particular, each such metric has geodesic flow conjugate to a Cartwright metric the one I discussed before, matrix of this type here. There the lengths of the closed geodesics were 2 pi divided by plus or minus alpha. So the shortest one determines the Cartwright metric, and therefore as a corollary of this, if you want a corollary of this theorem, is that, well, then they all look like Cartwright metrics, at least as far as the geodesic flow on the tangent bundle is concerned. Although the geometry itself can be quite different, and that's what I want to explain. So the geometry on the manifold itself can be quite different. So let's see. So what does it take to determine the geodesic flow? Let me start with that. Less than you might think. So what I'm trying to say is this really is a theorem about closed geodesics. That's the main interest. And I want to explain some of the ideas how to control the lengths of the closed geodesics in order to prove this theorem. So the geodesic flow now, so we're on the two-sphere, right? Geodesic flow goes from the tangent bundle to the tangent bundle. So that's a tangent bundle of S2. I can go from the unit tangent bundle to the unit tangent bundle, and the unit tangent bundle of S2 is RP3. Okay. So it's an action by the real line, if you want to, on the unit on RP3. Okay. And such actions are classified. They are, up to conjugacy, linear actions. In the following sense, if I describe as, say, a point x, y inside S3, inside C plus C, in R4, I want to claim that the action on RP3 is induced by a linear action on S3. It's going to write down the action on S3. It takes xy to e to the I a theta x e to the I b theta y. Where a and b are real numbers. So the geodesic flow is conjugate to this kind of linear flow, and now can descend to RP3 also. That's what it has to look like up to conjugacy. So how can we determine the integers a and b? That's the question. Where does in the geometry of the Finsler metric, how can I recognize the integers a and b? There are again two cases similar to our discussion over here. If a or b is irrational, then this generates a 2 torus. So I get a 2 torus action on RP3, and those are unique. It's a Cauchy-1 action. It's unique, and one can recover in this Cauchy-1 action the geodesic flow, which is now something of a certain slope in this 2 torus. So this case is the easy one, and corresponds to the case that in this case these geodesics are not all closed. Going through x, 0, and going through 0, y, they are of course closed, but generically they're not closed. If it's rational, that's again the interesting case. So then these geodesics all close up. In fact, they have a common period, 2 pi, and exception periods are 2 pi over a in this coordinate, and 2 pi over b in the other coordinate. So this means that such a Finsler metric in the setup can only have at most 2 exceptional closed geodesics. Okay. The case where not all geodesics are closed, like in the Finsler metric when the parameter was irrational, we already dealt with this argument that, well, in that case, this is just a 2 torus action. But if it's rational, I'm in a situation where all geodesics are closed. And now I want to control the length of the exceptional geodesics. That's the goal. Right? And according to this, it says that, well, if I know the length of the shortest one, then I should know the length of the other one also, and I should somehow determine it geometrically. So that's a challenge. Right? So it's really a theorem about closed geodesics. So we know they exist, we know that the period is what we want to know, but I have to compute the period geometrically. Okay. So how do you do this? I think I don't need this anymore. So the most basic property in the geometry of this such a manifold is the following. So geodesics, as I mentioned, have the same kind of behavior. Jacobi fields also do have the same behavior. Since the curvature is 1, a Jacobi field along the geodesic will be sine times a parallel vector field. Okay. In particular, it vanishes at time pi again. Every Jacobi field vanishes at time pi if you start at 0. So that means if we look at the exponential map at some point, and I restrict to the sphere of radius pi around the origin, well, all Jacobis vanish at time pi, so therefore the derivative of the exponential is 0 at this point, so it must be another point. Let me call it psi of p. So I have a certain map psi, which tells you if I start at a point p, every geodesic of length pi ends up in the same point psi of p. Okay. This implies, for example, easily that if pi 1 is 0, that M is diffeomorphic to the sphere by restricting the exponential map to a unit ball and then closing it up to a sphere. Okay. So these are metrics on spheres. Okay. So this map psi, this encodes a lot of information about the geometry. So let's call it Mn again. So maybe what's some property, say for every geodesic gamma, psi of gamma of t is gamma of t plus pi. Since every geodesic at time pi returns to the same point. So psi translates all the geodesics by time pi. So we assume that all geodesics are closed, but of course we don't know the period. So we don't know when we come back to the point. First observation is that psi is an isometry. So that's a very simple argument. Let me explain that to you. Take 2 points x and y, connect via the minimum geodesic, Hoff-Riemann folds of Finsler matrix. That has distance r, say. R is less than pi because all geodesics now minimize up to pi. That's another property. All geodesics minimize up to pi. Because the exponential map induces a diffeomorphism on the ball. That means that certainly they have no conjugate points, but better than that they can't meet. Because otherwise this would not induce a diffeomorphism with a unit sphere. And of course after pi they won't minimize anymore because that's a conjugate point along every geodesic. So now I can just run along the same geodesic. So say here is psi of x. Well, what's pi of x? It's simply gamma at pi, if this point is gamma at 0. Then I end up somewhere at psi of y. But that's gamma of r plus pi, because this is here as gamma at r. Well, that means that along this geodesic I go time r along this geodesic. Okay. But all geodesics are minimizing up to time pi. And this r was less than pi, so it's again minimizing. So this is from psi of x to psi of y is again equal to r. So it's an isometry. Right? And this isometry is very important. So I can maybe draw a little picture. It doesn't tell you everything, it tells you a few properties that you can try to use. So we're under 2 sphere, right? So remember in the theorem, we're going to assume that n is equal to 2. Although for this general story is 2 in any dimension, right? That's an isometry in any dimension. So in n equal to 2, I then have this kind of picture, roughly. I have my two-sphere. If I start anywhere at a point x, I end up at some point psi of x for every geodesic starting at x. What it does in between, there's no information. Right? It could do anything in between. But it has to end up at the same point psi of x. Okay. Of course, this can't happen. It can't have self-intersections because it's minimizing. So this is not a good picture. But it could certainly do the same. Okay, and unlike for the Qatar example, there's no reason why some equator should be a closed geodesic. Right? I don't know. And remember, the goal is that, well, we have a common period. Common period means that psi to some power is the identity. So all closed geodesics have length 2 pi p, because psi has length pi, p times z has length pi times p. I can say a little bit more. This assumptive psi must be also orientation reversing, right? So if I think of the assumptivity, it goes from x to psi of x. What does it do to the orientation? Take a geodesic and a Jacobi field. It goes to psi of x, and then they cross. So orientation is reversed. So actually, this must be even. Okay. So that's my common period, and now I have to somehow determine the length of the exception ones. And I know nothing in between, so this is a priori not so easy yet. Okay, so what can one do in dimension 2 that's special? There in dimension 2, we have, so from the uniformization theorem, it follows that every compact group acting on S2 is conjugate to a linear action again. So I can assume that psi is linear, but reverse orientation. So it says there exist polar coordinates. And I'm going to keep mixing up these. There exist polar coordinates. So somewhere, right, say theta and phi, such that psi of theta phi is equal to minus theta, because it has to reverse the orientation, but then there's a shift in phi. So phi plus, say, 2 pi lambda, or lambda is some real number. I can assume I change the orientation, possibly that it lies between 0 and 1/2. Okay. So now I can draw a little bit better picture over there. So I know a little bit more now because I have polar coordinates. So then, for example, it goes from the upper hemisphere to the lower one, if you want. So here's theta equal to 0. If I start here, psi of x down here. But I know nothing again in between. If I start on the North Pole, then psi of x is the South Pole. And notice that what this says, that what happens if I keep iterating. So I go from South Pole to North Pole, and then I come back to South Pole, after 10 pi, in fact. So here's pi, I go from North Pole to South Pole, I continue, I come back to the North Pole at time pi. But because of the angle, the tangent vector has a rotation by 2 pi lambda. So I don't come back to itself, it's not a closed geodesic, but it may bounce back and forth between North and South Pole many times until it closes up at time 2 pi p. So it's part of the geometry. And the geodesics in between that don't go through North and South Pole may be embedded or not. Okay, so that's our first improvement in dimension 2, that I know what the normal form of the isometry is. So we're going to use that strongly. And what I want to prove is the following, That's a very nice geometric proof. So every exceptional geodesic, so that means length less than, 2 pi p, prime length less than 2 pi p, I call this exceptional, just like in the Cartog metric, is embedded. Unlike the geodesics going from North Pole to South Pole, and have the following property. And two possibilities. A, it has length pi over lambda with w equal to 1. And B is it has length pi over 1 minus lambda with w equal to minus 1. So w is a winding number. Around North and South Pole. Okay. It's embedded, that means it can't go through North and South Pole because these are clearly not embedded. So it has to lie somewhere in between without ever hitting North and South Pole. But it says that the exceptional ones, they rotate once around North and South Pole, but in opposite directions. So the one that has someone looks like this. Then there's another one, I don't know where it lies, somewhere like this. Okay. It's embedded at least, and one winds around this way, and one winds around the other way. Where was it? Okay. Notice that in this situation here, a geodesic going the other way around is not a geodesic anymore, because the metric is not symmetric. Okay. It could happen indeed that these two closed geodesic coincide in the image, like in the Cartog example, where it's just the equator, but they're different, they count differently because their length differs. Okay. Okay. Let's see. So I want to say that, okay, we're over here. So there are two possible lengths that are allowed. So I'm now saying only what the allowed lengths are, pi over lambda and pi over 1 minus lambda. So pi over lambda would be, let's see, we assume lambda is rational. Right? So lambda is 2 pi p is a common period. So 2q over p. Right, this would mean the common period is 2 pi p. And then what is pi over lambda? That is 2q pi over p, and the other one, pi over 1 minus lambda, is 2q pi over 2q minus p, I guess. So these are the exceptional lengths. Here I divide by p. P could be equal to 1, so this one could also be not exceptional, but this here is a short one, and this cannot be not exceptional. There must at least be one exceptional closed geodesic. Unless lambda is equal to 1/2, that's a special situation. Then C squares the entity. Then I have a simple situation where I start at a point. I go to psi of x. I continue. I come back at time 2 pi. So all closed geodesic have the same prime length, 2 pi then. Okay. If you think of the circle actions on the RP3, that means it's simply conjugate to the Hopf action. The geodesic flow in that situation conjugate to the Hopf action. But there are many examples of this type that Robert Bryan produced. This already is infinite dimensional Finsler metric with this property, with all geodesics prime closed over length 2 pi. Okay. So now let's see how we can control this length. I think that's one nice part of the proof with a picture. So let's take an exception closed geodesic. I'm not going to show you why it's embedded. That's part of the proof here. So one has to show this first. Right, this closed trace is embedded. I take a point on this closed trace, it's called x0. And now look at all the images under this isometry psi of the point x0. Okay. They will be distributed somewhere along the circle in an even fashion. So here's x1, x2. This may not be psi of x0, but it can come back and many times. But at some point, they call it xm, which is psi of x0. It has to occur somewhere along this geodesic. Now continue, possibly, always with the same distance. And here say is xn minus 1, and this is xn. So the endpoints along this closed geodesic, which are images under the isometry psi, particularly each segment, so if gamma I is a segment, say, from xi to xi plus 1, they are the same length. And what's important for us that the change in the angle phi here, going around the angle in this direction, must be the same. So I claim the change of phi is the same along all segments. Just because they have isometry that takes one to the other, and the isometry preserves this kind of special polar coordinates, which one has to see, and that's not hard. So therefore, this picture is bad, right? The angle change is also the same from point to point. Let's call that A. So what does that mean? It means that if I go to xm, so the angle change, so m times A, so here I go up to time pi. Right? So m times A is what? Well, how do you know the address is embedded? It goes around north and south pole, right? So the total angle change must be 2 pi lambda, not 2 pi. Right, because along the closed geodesic, eventually I close up again at 2 pi lambda. So I have a relationship between my lambda, my angle lambda, that in some sense is an invariant of the Finsler metric. I call it the rotation angle because it tells you how much you rotate in the phi coordinate. Right? So this rotation angle lambda is related to the change in the phi angle. So let's see. Well, I forgot. My n is the first time I hit the image of x0 on the isometry psi. Okay, and m is the number of distinct points that I have on the closed geodesic. Okay, so I have to also bring in the winding number. Let's see. Okay, of course this is not correct. It's 2 pi w mod 2 pi, right? So I go around the closed geodesic. It winds once around the north and south pole. It cannot not wind around. W can't be 0, because then the change in angle would be 0. But the change in angle is m times the number a, which can't be 0. This also implies that I either go around in one direction or the other direction. Okay, and this will influence this inequality. On the other hand, what's the change in angle from x0 to xm, which was the image of x0 on the isometry? This is then m times a, because along one segment it was equal to a. Right? And this here consists of m segments. So, did I do this right? There's one integer that's not correct. This should be n. Right? I want to go around the whole closed geodesic. It consists of n segments. Right? Each time I change by an angle a along each segment. If I do this n times, I go on the whole closed geodesic, but it's embedded. So the winding number is plus or minus 1. So it's either 2 pi or minus 2 pi, depending on which way around I go. So the change from x0 to xm is n times a, and this is equal to so m times 2 pi w over n. Okay. So, of course, I'm going distance pi from x0 to xm. That's not information I have. So, what does that mean? That means that the number m times a, so that's am times, I go from here to here. Well, that's distance equal to pi. So, I must go along this geodesic up to psi, so that means that m over n times 2 pi w must be either equal to 2 pi lambda, well, either 2 pi lambda or 2 pi. Because this tells you what psi does. Psi shifts by 2 pi lambda, the angle, right? And here I go from x0 to xm, that's distance pi, so this must be, the psi must shift the angle by 2 pi lambda. So now I can look at two cases. So what does this mean? So two possibilities. One would be that m over n times w is equal to lambda. That means w is equal to plus 1. So I go clockwise around it. And then what's the length of the geodesic gamma? Well, each segment has the same length, right? What's the length of the first segment? Up to here it's pi. So the first segment has length pi over m. So length of gamma is n times pi over m. Right, from here to here it's pi. From here to here it's pi over m. I do this n times. So it's n times pi over m. So that means, let's put it together, that's equal to pi over lambda. Okay. So that's one possibility here. Pi over lambda with winding number plus 1. Okay. There's one more case which I won't carry out now, is that it could be that m over n times w is equal to 1 minus lambda. So it could be negative. Then w is minus 1. Goes around the other way. And then you can compute the length, it's pi over 1 minus lambda. So that's the proof. So you just look at the action of the isometry psi along the embedded closed geodesics. Okay. You're not done yet, because this only says that there are two possible exception lengths. I'm not saying that this exists or this exists, but I have to argue now that there exist exception ones, and if they are, then they have to have one of these two lengths. Okay. Notice pi over 1 minus lambda is the shortest one. And in fact, it has a length less than 2 pi, but bigger than pi. Less than 2 pi because lambda is less than 1/2. And so that's the length of the shortest one, right? And bigger than pi, since every geodesic minimum is up to pi. So it's a short one, has length less than 2 pi. And this one might be very long, depending on the rational number. So let's see how can I produce such closed geodesics. So the standard argument in Riemannian geometry, which works the same in Finsler geometry, that one looks at what I call displacement geodesics of isometries. So what is that? So let's say I have an isometry of my Finsler metric or Riemannian metric such that it has no fixed points for all x and such has a finite order. let's say K. Then I claim there's a closed geodesic which is invariant idea of geometry, which I want to call the displacement geodesic. So what's the argument? Looks at distance from x to f of x. Well, this number is positive since I know a fixed point. M is compact, so it assumes a minimum. Let that minimum be x0. So it's the distance from x0 to f of x0. So go from x0 to f of x0 with some minimal geodesic. And now continue, and I claim it can continue this way because then the image, f of gamma, would have an angle right here. If it had an angle, then going from midpoint to midpoint would be shorter than distance from x0 to this point here. Right? So this plus this would be shorter. So the angle, if I translate gamma to the next f of gamma, it can't have an angle. So the picture is here's gamma, here's f of gamma, here's square of gamma, and so on. And since it has finite order, I come back with fk minus 1 of gamma, and it closes up. Okay. So it's a displacement geodesic of an isometry. So we can try to apply this idea to the isometries we have, and the only one is psi or its powers. Okay. So let me just produce one in the last 5 minutes, namely the shortest one, which is supposed to be this one right here, which has a certain geometric meaning. So let's look at the minimal displacement geodesic in the sense over there of the isometry psi inverse. So I don't take psi itself, I take psi inverse. This is better in the following sense. So now I minimize the distance from x to psi inverse of x. So let's take our point x and take psi inverse of x. Let's say this distance is d of this displacement geodesic. You can also argue it must be less than pi. And now I can continue. So now I can go up to pi, say. So this here is psi of x. So that is now, sorry, let me do it like this. What is psi of this point right here? So let's continue here up to psi of psi inverse x, but that's x. So I must come back to x at time pi. So I go from x to psi of inverse of x, that's a small distance. I now continue up to time pi from this point. Since I'm taking the displacement geodesic of psi inverse, I come back to x itself. And this distance, by the definition of psi, is distance pi. Okay, this is a closed geodesic gamma of length d plus pi, which is less than 2 pi. So it's exceptional. Right, remember the common period was 2 pi times an integer. This is a short closed geodesic, must be exceptional because the length is less than pi. And according to our theorem, its length must be pi over 1 minus lambda. Notice that already I recovered the number lambda from the shortest closed geodesic. That's because I know its length now that determines lambda. The second closed geodesic, if it exists, would have length pi over lambda, so we're almost done with the theorem. Okay. I want to find a second closed geodesic, if it exists, which has these longer lengths, which is pi over lambda. Right? That's a long one. So here what I can do, I can look now at displacement geodesics of powers of psi. Each one has a displacement geodesic. You have to be careful. You have to choose a case such that it doesn't have a fixed point. That's one condition. It has finite order by definition. And you have to choose case such as not equal to psi inverse, because you already found that one. I also have to show along the way that the displacement geodesic for psi inverse is unique. Right? That's also part of the claim. So then I look at various powers and I convince myself eventually for large K I can choose it such that all these properties are satisfied, and then I get a closed geodesic which is not equal to the special geodesic gamma 0 here. That's the second way that must have length pi over 1 minus lambda, and then I'm done according to my general discussion that there can be at most 2 exceptional closed geodesics. So I determined them and I know what their length is. Maybe one more picture, that's kind of neat. What does this first geodesic look like? The displacement geodesic of psi inverse. Well, the distance from x to psi inverse of x, it's an isometry, it's a distance of psi of x to x. I minimize that, right? That's my, and then I take a geodesic that connects them. So I minimize the distance from psi of x to x. So what does that mean? Here's my point x. I go to psi of x with some geodesic, has length pi. Now I want to go backward. So in general there would be some very short one, but would have an angle there. This length would be less than pi. Okay. And now I simply minimize that among all points x. So I want to minimize the return time, going from psi of x back to x. When you minimize the return time, the effect is that this angle is going to be equal to pi, and then it closes up and has this length less than 2 pi. So that's another part of the picture. There are other details left which I'm not going to discuss, so thank you.
Questions?
If there is any Finsler net on S2 with a finite number of contours different from 2.
A finite number different from 2. No, I don't know one. I assume they exist, but so the examples finitely many are these kind of K-top type examples. I can also say start with one of these Bryant metrics where all there's a closed length 2 pi, which have a Killing vector field. Deform that, then I get say by an irrational multiple times a Killing vector field. I get again only 2 closed geodesics. So I have many examples of only 2, but I don't know one where it's finite and bigger than 2. That's a good question. Where are you there? Problem for you. Are you sleeping?
Any more questions?
So the injectivity radius is equal to diameter, right? All just minimize up to pi, not beyond that. So it's the same. So it's a Blaschke manifold, but it's not isometric to a round sphere. So it's again a counterexample to Blaschke in the Finsler realm.
More questions? I have one since the second of your talk. So when you said that you have the Finsler metric in dimension n, you said that you deform it, the Katok metric actually. You said that it also has curvature 1. Curvature in which sense? This is a Finsler metric, right?
Okay, so that's swept that under the carpet. So one thing that's special about Finsler metrics, so my unit sphere is a convex body. Here's the origin. That means that all the geometry is directionally dependent. Right, so in this direction and this direction, the geometry must be very different. Okay. That means that various other objects are directionally dependent. In particular, if I want to look at the kind of sectional curvature I used to, it must depend on not only the 2-plane, but also a vector inside the 2-plane. So it's called flag curvature. For example, I take a geodesic, that's my 1 vector. I look at some transfer to it, that's my 2-plane. But it will also depend on the direction of the geodesic. So it's a curvature is a flag curvature. For each flag, I have a number, and this theorem should be equal to 1 for any flag.
Okay. More questions? So thank you very much, Wolfgang.